Hello beautiful people. Today we'll continue with our topic of gravitation by distribution of mass, and we'll be looking at a situation whereby we have particle P. Let's draw it down. In your axis here you have particle P situated here, then you have a uniform rod. This is the center O of the uniform rod. Then we have an element dx there. Now we wanna investigate the gravitational field felt by P due to the uniform rod. Let's give the distance from P to the element there, R, and we can say our element, it's element dy. Then the distance from the element to the center, we can give it y, this distance over here. Then we can say from the center to the end of the rod, we'll say that's B, meaning the total distance of the rod will be 2b. Then we can say we have this line here from P to the end of the rod, which will be the same from P to the end of the rod that side. We can say the angle here, it's angle beta, the angle here, it's angle theta, meaning from P to the element dx, it's alpha. Then from P to the end of the rod, it's beta, meaning this angle here, let me write it with a different color. This angle over here, this angle, it's beta, right? When we analyze our diagram, let's say the distance x from there to there, meaning P is situated x distance from the rod. If you analyze our diagram, we'll get two triangles. This is our first triangle where we have our angle alpha, then we'll have R there. This is the R. Then our adjacent side to alpha, it's x. Then our opposite side from alpha, it's y. Notice it's y, not b. Then we'll have the second triangle here. Let me draw it in different color. This triangle, the second triangle, our angle here will be beta, this angle here, right? Then our adjacent, if you notice, the adjacent of alpha and beta are the same, so the adjacent is also x. But now the difference is for beta, it's not from P to element dy, but from P to the end of the rod, which is the distance b, meaning our hypotenuse will be b squared plus x squared, right? Particle P will experience an attractive force due to element dy. If we call that attractive force to be F prime, let's call it F prime. F prime is equals to, let's say the mass of particle P, mp is equals to small m, then mr is equals to capital M. There, those are our masses. Them. Then our element F prime will be G. The mass of dy. The mass of dy will be the total mass of the mass of dy here will be the total mass of the rod, which is m, times the height of dy, which is dy, all over the total height, which is dy, sorry for that, all over the total length of the rod, which is 2b. That will give you the mass of the rod, of the element dx, times the mass of P, which is small m, all over the distance between P and dy, which is r, then we square it, right? But now if you want to investigate the force that P experienced due to the entire rod, not due to element dy, we have to integrate this force F prime, right? But now if you notice, we have a force here, we have an element here. We'll also have and another element dy, which is situated at y distance from the center, somewhere there. Let's say that's our element dy, right? And this will be angle alpha and stuff, meaning we'll have a force which goes this way and a force that goes that way, right? This force will have an component, sine component, and a cos component. This will be f prime sine alpha, and this one will be f prime cos alpha. Same applies this side. This will be f prime sine alpha, and this one will be f prime cos alpha. Notice the sine alphas will cancel out, will be left only with the cos alpha. So we'll integrate using the cos alpha because that's the only force component that will be attracting P to the rod. So what we're going to do, we'll say our total force is equals to f prime integral of f prime cos alpha, right? But now we're integrating P, it's attracted by the entire rod, so we'll have to integrate from this point to this point. If the x-axis at the center of the rod, we can say from the center to this point it's negative b, since it's b, and from the center to that point it's positive b. So meaning in our integral we'll say we're integrating from negative b to positive b. If we substitute for our f prime, we'll have f is equals to the integral from negative b to positive b of g capital M dy small m all over 2b all over 2b r squared cos alpha. That's our force right there, right? If we're to sort try to write everything neater, make our force a bit neater, we'll have from our force there, it was f is equals to integral from negative b to p. We'll have g capital M cos alpha dy all over 2b r squared. But if you notice something from our diagram here, b is a constant which is the length, and mass and this mass are both constants. So we can take those quantities outside the integral, meaning this much here, these are all constant. We can take them out of the integral. We'd say f is equals to g capital M small m all over 2b integral of from negative b to b of cos alpha dy all over r squared. But now we are integrating in terms of y. We know that cos alpha changes is dependent on y, and r is dependent on y. But now in cos alpha we don't have y, and in r we don't have y. We have to go back to our diagram here. You remember these two triangles that we drew here? These two triangles, they show us that our x is equals to r cos alpha, and our r is equals to x squared plus y squared, root x squared plus y squared, using Pythagoras theorem, right? These are our two quantities. X is equals to r cos alpha and r is equals to that much. So if you come back here, we multiply the top and the bottom so that we can get r cos alpha, because we only have r here. We have to multiply by r, but we also have to divide by r. So we'll have our f is equals to g capital M small m all over 2b integral from negative b to b of r cos alpha dy all over r cubed, right? We said our r cos alpha is x, and our r it's root x squared plus y. So we'll have y is equals to g capital M small m all over 2b integral from negative b to positive b of x dy all over, which is y squared plus x squared 3 over 2. Now from here we can integrate, because we have our function in terms of a constant, which is x. X is just a distance of p from the rod, and the variable y, and we're integrating in terms of y. So now from here we can integrate, but this integral will be a bit challenging. So what we're going to do, we're going to use substitution. We'll say let y is equals to x tan theta, then dy will be equals to x. The integral of tan theta is sec squared theta d theta. After getting our substitution, we'll come back here. We'll come back to our formula. We substitute for these two quantities in our formula. We'll get that f is equals to g m, capital M, all over 2b integral. We said our x stays the same, but our dy, we have dy here, which is x sec squared theta, which is x sec squared theta d theta, right? All over, we had y to be x tan theta. Y is x tan theta, so we'll say y squared will be x squared tan squared theta plus, we didn't only have y squared plus x squared, but all raised to 3 over 2. If we try to simplify this, okay, before we try to simplify this, we must find the limit of integration. If we check our diagram here, we have when x will become b, y will become b when our angle is beta, right? And y will become negative b and when our angle is negative beta, meaning we have another triangle like that, sorry for that, which will be negative b, which will be negative beta, and this will still be x, which is the same triangle which is this triangle over here, right? So our limits of integration, which will be from negative beta to beta. If we factor out x here, we'll get that our f is equals to g capital M small m all over 2b integral from negative beta, not b but beta, of x squared sec squared theta d theta all over, this will be x squared into tan squared theta plus 1 all raised to 3 over 2. Then from here we know that this is an identity, which is x squared, and this one we can raise it to that much. We'll say we'll have our f is equals to g capital M small m all over 2b integral from negative beta to positive beta of x squared sec squared d theta all over x squared to the power 3 over 2. The 2's will cancel and we'll be left with x cubed. 10 squared plus 1 is sec squared. The squares will cancel, still will be left with sec cubed theta. These will cancel, will be left with x, and these ones will cancel, will be left with sec. Then we'll have f is equals to g capital M small m all over 2b, the integral from negative beta to beta of d theta all over x sec theta. But if we still remember, our x is a constant, so we can pull it out of the integral. Then we'll be left with f is equals to g capital M all over 2b x, the integral sec, will be left with 1 over sec. 1 over sec is still cos, so we have negative beta to beta of cos theta d theta. Then from here, from them, we'll get that, sorry for that, the integral of cos theta, it's sine theta, because the derivative of sine theta is positive cos, so the integral of positive cos, it's sine. Then we'll have our f is equals to g capital M small m all over 2b. So the integral of cos, it's a sine theta. Our limits of integration are from beta to positive beta, right? Then if we substitute our limits of integration, we'll have f is equals to g capital M small m all over 2b x. We have x here, don't forget that x. Then we'll have sine beta minus sine into minus beta. Sine of a negative number is just negative sign of that number. So this sign will come outside and cancel with this one and make it a positive. So we'll have 2 sine beta, meaning our f is equals to g capital M small m all over 2 bx into 2 sine beta. Right, if we go back to our diagrams again, we have sine of beta. This is our diagram here. Sine of beta. Sine of beta is a b all over this much. Right, so this one over this one, it's sine of beta. So we come and substitute it here. We'll say but sine beta is equals to b all over root b squared plus x squared, which are all constants. Therefore we'll have our f is equals to g capital L letter M small letter m 2bx. All these 2 will cancel over here, so we can ignore that 2. Then we'll have b all over root b squared plus x squared. Then these 2 p's will cancel them. We'll have that our force, the force felt by particle p, is equals to g capital letter M small letter m all over x root b squared plus x squared. Right, so this is the force of attraction.